So we can ask the question, how much carbon are ecosystems accumulating? So on an annual basis, after all of the photosynthesis and all the respiration is done, how much carbon has that ecosystem accumulated? These are maps of predicted NEE based on some regression models. The units on this, since it's NEE, is going to be grams of carbon per meter squared. These are also measured on a seasonal basis. We're going to have spring, summer, fall, and winter. If you know the units here, grams of carbon per meter squared, my guess is per 3 months. Positive means a net source, negative means a net sink of carbon. And you can see in the spring, which here is March through May, that a lot of these ecosystems are still going to be net sources. They just haven't leafed out yet, and so you're not going to get a high acquisition of carbon, as opposed to these more southern ecosystems within the US that have a lot of leaves already and are going to photosynthesize at a high rate. By the time summer rolls around, the whole eastern part of the US has a lot of leaves, and that's at the height of photosynthesis relative to respiration. Fall comes, and then you see a different pattern that's more similar to what we have in spring. A lot more loss in the northern ecosystems, southern ecosystems still gaining, and then in the winter there's just a few ecosystems that are evergreen, for example, and still fixing carbon. On the west coast, you can see that these ecosystems here in the spring are still gaining a lot of carbon, whereas these north central ecosystems that don't have leaves aren't. So good temperatures, lots of moisture still around, you're going to have gains of carbon that are different in these systems and these systems. So some of this difference here is between north and south is due to temperature. Others are moisture patterns here. When we have a lot of winter precipitation, you're going to have a different season of net photosynthesis and negative NEE than you will in the more continental deciduous system. Now, another factor for thinking about NEE is a successional pattern. And we can think about forests as they regrow, how much carbon they accumulate, and how much time for a forest is associated with net carbon growth. So, for example, if you have small trees growing, they're probably going to fix and hold on to a lot less carbon than a forest with big trees. But as that forest ages, a lot of those trees fall over and die, and their carbon will get respired. So one of the questions that we might have is, what does a curve look like for net ecosystem exchange or net ecosystem productivity for forest? So how quickly do they increase in their rate of NEP, what the peak is, and then when does that start to decline? And is there a point when forests become actually a net source of carbon and instead of a net sink? This is really important because a lot of forests are regrowing after having been recut earlier in the 20th century. And as those forest stands age, it's important to ask whether they're still accumulating carbon, or whether from a carbon perspective, cutting that forest down, taking the wood and using it and allowing it to regrow would actually store more carbon. Empirically, when we take a look at the patterns of net ecosystem productivity, and again, units here, kilograms of carbon per meter squared per year. So multiply it by 1,000 to get grams of carbon. So 400, 800, 1,200. A positive number for net ecosystem productivity means an acquisition of carbon. So we're looking at 400 grams, 800, and 1,200 grams of carbon per meter squared per year being sequestered or stored in the forest. On the y-axis, we have stand age. And this is on a log scale. So we've got a 1-year-old stand, 3, 10, 31, 100, 315. So each of these units is roughly 3. Each one of these points is a different forest on which net ecosystem productivity was measured. The line shows the average value of NEP, and it's somewhere on the order of 500 forest plots. The pattern looks something like this. So peak net ecosystem production, somewhere on the order of 500 grams per meter squared per year, occurs at an intermediate age. That might be something like 25 years. And it declines after that, on average. But you can see that it's still relatively high, even out somewhere on the order of 200 years. So, we don't have a situation where it's something like this, so that once a stand hits 100 years, it doesn't start to respire more carbon than it gains. And that period of accumulation of carbon for forests actually extends pretty far out into the hundreds of years. So even in a forest that's 200 years, on average, is still accumulating almost as much carbon as a relatively young stand. These set of figures show the correlation of carbon fluxes with different environmental factors for forests in Europe. Now, the panels on the left are for southern forests, the patterns on the right for northern forests. The y-axes are either GPP, gross primary production, grams of carbon per meter squared per year, ecosystem respiration, grams of carbon per meter squared per year, and net ecosystem production, grams of carbon per meter squared per year. And again, GPP minus ecosystem respiration is net ecosystem production. So this is just the difference of these two curves. Now, the reason that the authors show this is to show that different environmental factors can determine carbon fluxes for different ecosystems. So among these forests in the southern Europe, GPP, ecosystem respiration, and to a degree net ecosystem production are associated more with water availability. And this x-axis is an index of water availability. It's a ratio of actual to potential evapotranspiration, which tells you to a certain degree how much surplus water there is in the ecosystem. So in the southern forests that tend to be pretty warm, it's the wet forests that have the highest GPP in ecosystem respiration, and to a degree, net ecosystem productivity. The dry forests have the lowest GPP and the lowest rates of respiration. In the northern ecosystems that tend to be colder on average, it's really a temperature gradient. So it's the warm systems that have the highest GPP in ecosystem respiration and net ecosystem productivity. On the other hand, these cold ecosystems, low GPP, low ecosystem respiration, and lower net ecosystem productivity.